Hi, welcome to another video. Today I'm looking at an Electro-Voice ELX118P, designed and engineered by Electro-Voice, Burnsville, MN. Is that Minnesota, USA? So designed in America, built in China. This subwoofer amplifier was sent to me with a ZLX15P. I repaired that amp, sent it back, repaired. I thought I'd dig this out. As I say, I've had this a number of years. So here's a look at so we've got an input, link output, so presumably you'd run your full range in here, XLR. This would go out to a full range speaker, knocking off the bass. You can turn the logo on and off, and obviously the input and equalization. So that's a look at the back. I've not plugged this in, so we'll look at it together. This is a look at the other side. So this is obviously the power supply. I see one difference compared to the ZLX12 and 15s. They had uninsulated main switches. This one's insulated. And you see a load of Loctite everywhere, Loctite on the earth. So this has got more insulation than the ZLX12 and 15Ps. There's a fuse, and the cover's not been lifted yet. I don't even know if this fuse is blown. So to me this looks quite a small power supply. I had a look earlier. The specification for this amplifier, they quote 700 watts Class D amplifier. They don't say if that 700 watts is peak or RMS. Well, I'm going to repair this and we'll put it on the scope and we'll find out. So 700 watts, at least they're not quoting 1000 watts, like those ZLX12 and 15Ps, which are nothing like 1000 watts. So this is the power supply. You can see it's a Class D because we've got two coils here, one there and one there, and each of these boards has two FETs. So I'm assuming, like the ZLX12 and 15s, I'm assuming the amplifier one half does a positive half cycle, and the other board does the other half cycle. The 450 version 2 only has a pair of FETs for all of the bass. This has got 4, so this should be super reliable, and we should be able to get most of that power out from the power supply into the woofer. So I can't wait to try it. The coils are smaller because they're housed in a ferrite core. That means you can get a large inductor into a smaller size, in case you're wondering. So we've got two potentiometers on each board. I've no idea what those potentiometers are for, and no idea how to adjust them. You'd have to put it on the scope and see what happens when you tweak them. It looks like the output for the speaker is here, so low frequency. These boards, you can see there's HF, so that board's obviously used somewhere else as well. And their logo, plug here. So on this power supply, sort of mains comes in. These are the smoothing capacitors. So here in the UK, 240 volts, rectified and smooth, we'd have 320 here. Just spot another plug there. It looks like you link this plug here if you want to run it on 115 volts. Not sure if you can see in here. You link the plug for 115 volts and do not link it for 230. This 8-pin chip is obviously the driver. For these, looks like two FETs here driven by a transformer. So it looks like, at a glance, without testing it, I'll test it in a minute, it looks like having two FETs on this non-engineered plate, it looks like this could be a push-pull, which would make this quite powerful. So maybe two FETs here, but then if those two FETs drive this transformer, like push-pull on the primary, you'd have a number of rectifiers on the output, but there's 4 of these transistor cases here, so I'm not sure, are they 4 rectifiers or 2 FETs and 2 rectifiers? if they're 2 FETs and 2 rectifiers, then what are these over here? I was looking at this, so they've got simple spaces holding these 2 boards apart, but then it's not actually that straight. This joint here is pressed down, these connectors here, they're pressed down and squashed, bending the board slightly. I didn't like this setup. It looks like there's some sort of microcontroller here. That's probably just an op amp. Not sure about these other cases, whether they're different regulators. We'll have to have a look. It says definitely a microcontroller and a crystal. That crystal is going to run that microcontroller. There's a few spaces for a few op amps not used. Another op amp down there. Another component missing, or a few components missing there. So it's looking like they may use this microcontroller to separate the bass, to filter out the bass from the full range. I think this is something like 32 Hz to 130 Hz. So it's a complicated method. There's easier methods just with a few op amps, but so it looks like they've got a microcontroller to separate the bass. I think the first thing for me to do is plug it in and see have we got any power, because I've not tried it. I thought this was a crack while I was looking. That's just silicon up the side of this component. So I just had a look at these 2 components under the magnifying glass. These are UC38M33Gs. So as yet I do not know what they are. The UA78M, that looks like a positive voltage regulator, but I'm not familiar with the number. UA78M33. So we'll have to look at these. Can't see these. So these are tip 31 and tip 32. So they are complementary NPN and PNP silicon transistors. Simple power supply, 2 amplifiers. The signal is all derived from this board. Yet I see the whole lot is something like 700 odd pound. Leave a note in a comment if you got one of these. How much did you pay for it? I'll plug some power in and we'll see if we've got anything here. Right, here's a power lead. That's not obvious, is it? Which is on and off. If you press that one, is that one in for on and that's off? Questions already. Right, power. In fact, so we're going to have no power light other than this switch lighting up. The logo light is on the front of the case and I don't have the case. So there's nothing on here to tell me if it's powered up other than this switch. Right, that turns on. And absolutely nothing to tell me if it's dead. So if I sit this on my solder just to prop it up. So I need to establish, have we got power here? And for that I need to establish a ground. So I'll get this meter in view. So first of all what I'll do, so I'm on DC, have we got any power here? So this piece of metal, do you see the bar on the meter fluctuating? There's some sort of signal on this metal, so that's not insulated. This one may be, but this one isn't. Is that AC? It's like it's pulsing. 96 volts AC. Wow. So that could bite. So we've got 96 volts here. Back on DC. Can we find a ground or power? So just keeping this on earth. Nothing on the red, nothing on the black, nothing, 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 nothing. So let's draw it this way. Nothing, nothing. I'll turn it off for a second and unplug the power. Put this on continuity. I'm wondering, are any of these attached to ground? No. 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 Oh, that one. So this is a ground, that black one. Right, so I'll plug it back in. Turn it on. So this black one here, hopefully you can see it, that's definitely a ground. And we definitely have nothing. No. So if I very carefully, I don't know if you can see, this plug up here looks like the lower voltages, maybe plus minus 15. So with respect to ground, if I just probe this red lead at the end, 0.4, negative 0.4, without shorting anything out, nothing. Go on the end, yeah, nothing. So at the moment it looks like this power supply is dead, but I haven't checked the fuse. Turn it off. Let's use a screwdriver. So it looks like you unhook these to lift them up. Or glue down a cover that snaps into place. Great stuff. Right, continuity test. Oh, that surprised me. So we have got power. But no harm in double checking. But then of course we got power because I measured 90 volts AC here. So I need to take this power supply off and start looking at these components, see what they are. Something's going to be blown on here. I've not looked at this device yet, or whether it's available, and I've not looked at these 4 devices here. I'll take this power supply off and come back in a minute. I had a sudden thought, could it be something on this lot? To the left of the power supply, short circuit, and the power supply is actually protecting itself. So just before removing this board, I unclipped this and thought I'd give it a quick check. And I think I saw a voltage on that red line. So if I keep this on the case, which is ground, so we had nothing. So by unplugging this, I'll look. Oh, so it's 40. I was thinking it was AC then, but it's telling me it's a high voltage, so 42.7. So the black is obviously ground, blue -42. So that's actually good news, because I know nothing about this power supply. It means I don't have to start looking at these components. So we've got +42, -42. 19 is on the black at the end, and the yellow is nothing. Not sure if that's right. So that's definitely 20 on the black. So you can call that 43 and that 43. So plus and minus 43 volts. So it's not 700 watts. It's not 700 watts peak. It's more powerful than the ZLX 12 and 15s, because they had plus or minus 36 volts of supply rail. This is higher, and since you square the voltage, this is going to be more powerful than the ZLX range. I'll show you on the calculations when we get it working. So this looks like there may well be a short in one of these base drivers, which I'm shocked, because each base driver has got 2 FETs, not just one. Oh look, and those 2 tip transistors I'm on here, another case, 15.2 on one and minus 15.2 on the other. So they're the plus and minus 15 volt regulators. No heat sinks, notice. And they're hot. I can keep my finger on it, but yeah, I can keep my finger on it, but it's hot. So it's not going to burn me, but it's hot. That other one to the left is hot, and this other one's hot. So they're all hot. No heat sinks, just semi floating about on the board. So these ones, not sure if you can see, yeah, these ones here. I was dabbing it quickly because although this might have 15 volts, it could be with respect to minus 127 or something, so this could potentially have had over 100 volts on it, but they haven't. Yeah, so these are hot, and that one's floating about. That silicon's done nothing down there. That's warm, hot, and that one behind. So plus and minus 15 volt regulators. I need to take off one of these boards, or both. Looks like they just unplug. And I'll take these boards off and we'll check the FETs. So I was wrong about these. I thought these screws went straight through this panel onto the other side, but they don't. There's 2 screws there for one base channel, 2 screws there for the other half. They come through this threaded metal plate, which is nice. They've got these captive nuts, and then you've got these countersunk screws in there holding the FETs. So it's not as bad as I thought it was, but simple to take off. But boy, look at that lot. So here's one. I've taken the screws out on this other one. Let's simply unplug. I don't like these connectors in audio stuff. You can get dirty joints over the years. Let me clean. I'll clean the heatsink compound off of this, and then we'll test the FETs. See if we can find a short circuit. So here's those 2 boards. I haven't tested the FET yet, but notice the brand name, Hypex. Now, Hypex are a company in the Netherlands. they make little modules like this, 200 watt amplifiers. So this would be 200 watts and this one would be 200 watts. Presumably that's peak music power. So 200 plus 200, so 400 watts peak music power into that sub. And you can buy modules like this from Hypex Electronics BV. Have a look on the internet. I'll show you a picture here of the PDF. So these aren't designed by EV or Bosch, they're designed and built by Hypex. So if the drivers on any of these boards are gone, there's going to be little chance of me finding the correct component that drives those FETs. But notice on this one, this large resistor is at 0.5 ohm. Look, that one looks blown. Hopefully you can see that. So this looks like the faulty one. This one looks okay. So we might have half an amplifier working. Let me see if we can test these FETs and ascertain are these one or more of these FETs blown. So I put my meter on Diode Test. Right, so this is tricky because they're small. I'll do this blown one first. There's some little tabs down the bottom. So here's one transistor here. There we go, that's a dead short. Dead short. Dead short. Blown. So we've got half a volt between, so we've got 0.6 of a volt between that junction. And half a volt there, or 0.6. So that one with the blown resistor, this has definitely got two short circuit FETs and one of these resistors is blown. So look, I was standing up for EV, thinking these were EV, but they're not. They are Hypex Electronics in Belgium, also in Netherlands. And I thought they're a quality design because they're two FETs doing the job of one. So I thought these should be rock solid, and clearly they're not. Unless of course the woofer is going short circuit. But then I understand, reading some of the literature for these, they've got a current limit of 10 amps. If you exceed the supply voltage, unregulated supply voltage of plus or minus 56 on their off-the-shelf units, they will cut out. So they protect themselves to a degree. So you would get audio coming in on two of these pins, and it would simply drive the positive half cycle and the negative half cycle, and start oscillating at roughly 400 kilohertz. So it's disappointing. It's not the power supply, because the power supply has only got, there's a couple of FETs and one FET driver. This has got a ton of surface mount, tiny stuff that I'm probably going to be unable to find if it's blown. What I'll do, I'll pull these FETs out. So one FET there, one FET there, and pull this resistor off. Looks like half an ohm. Shall we measure it? I'm not sure why they've got these small resistors, unless that's a current sense, so it limits the current to protect themselves. But then this one's obviously not worked, so if I touch the probes, so we've got point 1, 0.2. Huh? Right, 0.2, 1.4 million. So I think they're half a 0.5 of an ohm. And then this one, obviously with the resistance of the leads, 0.1, 0.2, these are significantly lower resistance than these leads, so 0.2, 0.2. So that's blown, and it hasn't limited the current, and the FETs have gone short circuit. But let me get these FETs out. And just looking, even taking the FETs out, in case you think this is easy, it's not. You've got to heat this lot up. Heat all this up. It's through plated. Heat this lot up and pull 6 legs out without upsetting any of these surrounding components. And I'm looking at that one there. That looks like is that an 04, 02 component? These are 06, 03, so they're small, and there's even smaller ones in there. I think these are 04, 02s. Unless these are 06, 03 and they're 08. There's some very tiny components on here. Smaller than what I'm used to dealing with. I can manage 06, 03s, that's about my limit. Anyway, let me pull these FETs out, see what they are. Well, for the beginners, I'll show you how I take transistors off these types of boards so you don't damage the board. The last thing you want is one of those desolder stations. It'll just destroy those tracks, and you can't get it in there with the surrounding components. So add some fresh solder to this heatsink to conduct the heat. I'll put a big tip on my soldering iron. Now I've got 2. Heat this up and pull it away from the board without getting burnt. Nearly. Let's try the other end. There's no rush. Hopefully I'm keeping this board in focus. It's difficult, this camera's in the way, but this is just taken off the heatsink. Now I've got that gap. Keep some pressure in there. Not quite off yet. Now I need a bigger screwdriver, which I haven't got one here. There we go, one. And next door's dog always starts barking when I turn this camera on. Just about out. So I've taken a heatsink off without pulling through the through plating. And now the trick with these transistors, we know they're both destroyed. So my recommendation I do recommend this. Chop the transistor off. 1, 2, that off, it's stuck on with glue. Right, this heatsink compound off. Right, fresh solder, and not keep your iron away from these capacitors. Put some fresh solder on. It's easy and you won't destroy your board, if indeed it's repairable, which I don't know yet. Right, can I do this and keep you in view? It's difficult. I could do with a third pair of hands here. I wonder. Mind my coffee out of the way. I've got an idea. Here's a pair of hands. There we go. Put that on there. Right, this should work. Wait till it moves, and it's not moving. There it goes. One. 2. Keeping away from this capacitor under the iron. Can't get in at this angle, the camera's in the way. 3. 4. Only grab it when it's hot and moving. Actually, I remember some of these tracks are thicker than the others, so I think the tracks are taking away the heat. 5. And last one in there under the glue, which you probably can't see. This has obviously got a smaller track because it's coming off easily, so the track on the other side is not sucking the heat out. That's the 6 pins removed without damaging the tracks. Now all I have to do is get some solder wick on there, put fresh solder on, put some solder wick and clear those holes once I've got the new transistors. And I'll probably put a heat gun on this resistor to get rid of this resistor, except notice there's a large track here that's going to suck away the heat, but I can worry about that later. So the question is what are the value of these FETs? Well, so they're ST microelectronics. I'll have to have a look under my magnifying glass. It looks like they are P14NF12P. So the 1.4 I'm thinking is maybe 14 amp, and the 12P is 120 volt. I think it works like that, unless I've got that back to front. 14 amps, 120 volt, which sounds right for a base circuit. Let me see if these are available. I'll put the number on the screen. Here you are. I was actually right. So STP14NF12, 120 volt between drain and source, and 14 amp continuous drain current, and they've got an RDS on resistance of 0.18 of an ohm. Since these FETs are fully insulated, that limits the power they can dissipate. So for the insulated, they can only dissipate 25 watts, and uninsulated 60 watts. If you go for the uninsulated, you've then got to use the top hats for the screws and mica washers to insulate it from this. Swings and roundabouts. Yeah, so I said this amplifier's got two pairs of FETs as opposed to one pair on the 450 Mackie. So obviously this has got the full signal coming in and it's driving the positive and negative rail up to the supply or near the supply. But since it's two amplifiers, that's got to do, this one's got to do plus and minus, and then this one's got to do the plus and minus. They could have designed it in such a way, if they'd designed their own amp, just get one transistor to do the positive and one transistor to do the negative. So I was thinking, since there are two, it's going to be better. This has got, so effectively two transistors driving a plus and minus 43 volt rail. The Mackie 450 base driver is two FETs driving a plus and minus 75 volt rail, and that base circuit on a 450 version 2 is super reliable. They do sometimes fail, but nonetheless they are super reliable, and it's handling twice the power of these. I'll see if I can find some FETs and I'll temporarily bridge this resistor with a bit of wire. I'll have a look at these FETs, find out which pin is the gate, and see if the gate resistors are okay. If they are, we're in with a chance. Here's a quick look at some of the specs of those FETs. Total gate charge 15 nanocoulombs. That is exceptionally small. So gate to source charge 3.7, gate to drain 4.7. So it does not take much charge or much energy to turn these FETs on. So unlike some of the other transistors I've come across, this is unlikely to ring on that PCB. Right, so I put fresh solder on these holes for the FET transistors and simply put my soldering iron on, solder wick, I like this chem wick, and I've cleaned those holes. This resistor, I'm really worried about putting my heat gun on and damaging surrounding components or disturbing them, heating them up, and maybe they slide away. So I've started heating this large resistor up, the blown one, with my soldering iron, and this end is just lifted. So if I show you what I've been doing, put some fresh solder on. It's difficult, this camera hasn't got macro, so I've got a big tip on here because of that large track. I simply kept the heat on this side and started lifting and bending this resistor. So we then hit this side and that's it, it's off. And for those of you who are interested in how these FETs are driven, I thought these resistors here, I thought they were 28 ohms. I thought, well, that's reasonable for a gate drive. No, these are 2.2 ohms. And if you've seen any of my other videos, you will understand 2.2 ohms is an exceptionally low resistor to have on a gate drive. But now we've seen the specifications of those FETs. They require a low gate charge, so they're not likely to ring, but having such a low resistor increases the chance of them ringing. Anyway, those 2.2 ohm resistors are driven from some PNP transistors. This one here and this one here. I've tested those, they're not blown, not open circuit. They turn the gates on, and this diode and this resistor and this diode and a resistor somewhere else, maybe here, discharges the gate. So since these gate resistors are really low, I've got to be careful of the FET I put in here. If, like when I was repairing one of the PVs, if I just come along and pick up a random FET with a high gate charge. Once that gate charge has charged, it's going to bring, and this will overheat, and those FETs will blow up within seconds of turning it on. What I'll do, I'll flash up the screen if you're interested. Flash up the screen now, and this is the video you should look at if you're interested in why FETs would start to bring, or certainly what brand of FETs would start to bring. So you can't just put any FET in there willy-nilly and expect it to work. So with such a low gate resistor, you've got to be careful on your choice of FETs. It's got to have a low total capacitance, it's got to require a low gate charge, and it's got to have a low gate to drain charge. Otherwise, as I have experienced, you will run into problems. I found some FETs I can use in here. I'm using the STF15NM65, 650 volts, 12 amps at 0.35 ohms on resistance, so twice as much as the originals, but it's all I've got to hand. The original ones are now obsolete, and I will probably eventually have a look for some alternatives, but I'm going to see, can we just get this to work with these FETs. So these FETs, again made by ST Microelectronics, STF15NM65, they have a low gate charge. It's still higher than the originals, but it's a low gate charge, low gate to drain and gate to source, but higher than the original. So you have got to put these on the scope and see, have a look, are they performing? Make sure they're not ringing. So I've put a link in place of that surface mount resistor that I think is a current sense, but as well as being a current sense, it obviously acts as a fuse as well, although didn't stop the power supply going into current limit. So bit of wire for the resistor, 0.05 ohms is that bit of wire, and then 2 transistors that I've just got to solder up. And I've seen some poor soldering skills on YouTube. It's a big tip, because this middle track is big, so I've left my big tip on there. Put a small bit of solder on your iron, offer it up, and then pour in some solder quickly and take the soldering iron away before you cook the component and overheat the solder. It's difficult with this camera in the way. As you can see, I'm sitting on that capacitor at the moment. Got to be careful not to damage that or short it out. And the last pin, which I believe is the gate. So it needs lots of heat because they're through plated. You want the solder to go all the way through the board. So that looks good. Chop off the legs. Right, so other than taking off the flux residue with a cleaner, this is ready to go back in. Right, so the repaired one is on the left here. I'm not going to screw them down yet, make sure it works. make sure we haven't got this power supply going into current limit. So the first thing, connect the power supply. Get rid of that for a minute. Right, power supply back on. So first things first is hopefully it's not going to go pop. So where's the mains lead? Please don't go pop. Right, power. Moment of truth. Right, no explosions. But have we got power? Fingers crossed. Because it is literally fingers crossed. Right, I'll put this on the case. So remember we had nothing before. And we've got nothing. Oh no, I didn't have it in correctly. So 41 plus 41 on the red. We know this next black is ground. Blue minus 41. So that's good news. This next black 19.4. Yellow nothing. Let's check the 15. Don't know what this camera can see. I don't know if you could see that meter as well. Sorry if you couldn't. So now I'm going to see, have we still got the plus and minus 15 on these? Have we still got the plus and minus 15 on these up here? Put the solder behind it. Can you see? Yes. Right, so this on the case. Hopefully you can see the meter. I'll turn that light off. Stand the meter up a bit. Turn the light on for you. Oh, wrong one. Right, now I can see the meter, so plus 15.1, and without shorting them out, minus 15.1, and my phone just made a noise. Always worries me when I'm testing stuff for the first time. And put this back on the power supply over here so you can see the meter. 41.4 ground. Blue is minus 41. And 19.3, so call it 20 on that inner black one, if you press hard. So that's the good news. 2 new FETs on here, and the power supply is no longer going into current limit. So straight away it's a good power supply because it protects itself. I now need to get I've got an 8 ohm resistor with a couple of spades used for the SWA 1501s. They require an 8 to 12 ohm load. I'll go and get that and plug my scope in, and we'll put a signal into this amp. See if we can get some sine waves out of it. Back in a minute. I thought this resistor was 8 ohm, but it's not, it's 12 ohm. So that's doing this amplifier a favour. See what power we can get out of it with 12 ohms, which is easier than driving a load into a 4 or 8 ohm. So since there's 2 channels, 1 channel there, 1 channel there, there's the leads connected, power is on, Right, I'll set the level on the amplifier to halfway. Can't believe the battery on this Sony camera just ran out, so I've plugged the power lead into a portable power pack. See if I can just test this amp and get it out of the way for the night. So I've turned the signal generator on. This is one probe. I've turned the bandwidth limit on because I haven't got filters to take out the 400 kHz, just a sort of 1k resistor and a couple of nanofarad capacitor. Normally works as a filter. Turn the second channel on. So we are on 5 volts of division. So it's a subwoofer. So turn the frequency down to something like 100 Hertz. And we want to see a signal on both of these. Oh, there it goes. So that's the frequency response. The top end, look, is just coming in at 150. So let's turn. So the noise is because I haven't got the 400 kHz filter on the resistor. Well, that's looking okay. As we turn the volume up, the 400 kHz will become less relevant or less dominant. So I'll turn the volume up on the amp first. Right, that is full volume on the amp at 75 millivolts input. So again, less powerful than the 450 version 1 and version 2. Well, my camera is still on, that's good. Right, so I have to turn the volume up here then. So if we set that, actually, so they said something like 32 Hertz to 130 Hertz. So if you look at this amplitude, that's dropping at 41 Hertz, or coming up above 41 there, 45. So it's not 32 Hertz, it's amplifying 38, but lower, as a lower amplitude to the 41. So its peak response is actually closer to 41, 43 Hertz, and it's dropping, so 40, call it 48, 47 Hertz seems to be its peak response. Now I'll turn the volume up. But I don't want to blow this amp up after just repairing it. Right, now we're getting up there. Turn the scope down, 5 volts of division. Now you can see the 400 kilohertz is less dominant, less of a problem. Turn the volume up. And the volume on the amp, on the sub, is turned right up. So whilst I think of it, those replacement FETs are working fine. I'll put the number up on the screen again. So 300 millivolts input, look. We've got 21 volts peak to peak on each amplifier. -10 volts a division. Remembering this power supply, we only measured plus or minus 43. But I do not want to blow this amp up. Let's turn the frequency up a touch. Leave it 60 Hertz. Well, I'll turn the volume up. In fact, what I'll do, I'll turn the amplifier down and my resistor is getting very hot, so I can't leave it up long when I do turn it up. Once I've turned the amplifier down, let's turn this right up. Well, there we go, 1 volt peak to peak, just there. Hopefully you can see it. Well, I will now turn this amplifier volume control up quickly. Oh, I saw it shoot over 51 there. Right, let's turn these down. 20 volts a division. Oh, that's it. That's maximum there. 59 volts peak to peak. Well, let's turn this resistor. Yep, red hot, probably burning my scope probes. I'll turn this up even more. 1.5 volts peak to peak input. Oh, 75. Oh, did you see it? Right. See it going square there at 74 volts. So call it 69. Call it 70 volts peak to peak. And something's smelling awful. It smells like fish, actually. And I don't like fish or anything that lives near puddles. Right, so it's still working. So I think you saw that 60 volts peak to peak. We'll give it one more go. Actually, this resistor is red hot. Ah, that's what was smelling. My mat. See what I do for you guys? Melt my own mat. And as I say, this is a 12 ohm, so it's doing the amp a favour. It's not a 4 or 8 ohm load. I've messed up my mat. Remember this time and day. Now I know where the fishy smell was coming from. So we need to concentrate. What maximum voltage can we get out of this before it's clipping? So I've got, right, 74 is the max, but it's very distorted. 68, 69. Right, it's squaring off there, 73. So that's bad, it's not actually protecting itself. So 63 peak to peak on both channels, 64, 67, 68. Oh, I've got smoke coming here. Is that resistor? No, it's starting to square off there, so we'll call it 70 volts peak to peak into a 12 ohm load. It's going to be worse at an 8 ohm load. You probably wouldn't get that supply. So let's do the maths. Right, here's one of those transistors, the original ones, STP14NF12FP. STMicroelectronics, obsolete. So to answer all the questions, what will the speaker see across this 8 ohm load? Got a 4 ohm resistor here and a 4 ohm resistor here. So I'll take my scope probes off and put this pico differential probe on, which means I can put this negative probe on one end of the resistor and this positive probe on the other. So this pico differential probe will see the voltage that the speaker, the woofer, sees. Right, so the scope's on 20 volts a division. Turn my differential probe on. I've got to be quick with the power at full power because the gold resistor gets very hot, since it's only a 100 watt resistor and we are pumping roughly 300 watts into it. 50 Hertz, 48 volts peak to peak. Oh, there we go, 140 odd, starting to square off. So I'm going to come down. I'll call it, so I'll do that once more. 140, it's starting to clip. So I'll come down to 135. Quickly turn it off. And these resistors are, well, the gold one is very hot, the green one is much cooler. I'll give it the benefit of the doubt. I'll use 135 volts peak to peak. That is what we see across the speaker effectively. That's peak to peak. So divide by 2, 67, which is close to the 70 I was using. 70 volts peak to peak. So that's half the peak. Multiply by 0.707 equals, to find the RMS. Multiply that by itself, so 47.72 times equals 47.72 times 47.72, 2,277. Wow, that sounds high, doesn't it? Divided into 8 ohms equals 284.67 watts RMS. Now that is the maximum continuous real power from this amplifier. So now you've seen two methods of measuring the real power from this Electro-Voice Sub-Woofer Amplifier. So I know what will happen if I don't test this on a 4 ohm speaker. Everyone's going to shout. Now 8 ohms is this, so 4 ohms double the power. This is what happens when I connect this sub to a 4 ohm load. Differential probe, both ends of this 4 ohm 100 watt resistor, but substantially larger than that gold resistor. So it's wire wound, so it does have inductance like a speaker. The EQ button over here doesn't make any difference. It actually boosts the signal there, but the cutout is the same. So I'll just leave it flat. This is 1.5 volts input. I think I was looking at the specifications of a Yamaha mixer that a friend DJ uses. His Yamaha mixer only puts out 1.5 volts maximum, and this sub requires that full voltage to get max power. So the front end is nowhere near as sensitive as the Mackies. So this is 50 Hertz. I'll wind it up slowly. Look at the peak to peak voltage over here, So 35 volts, 55, 56. See this? If I turn it up a touch more, boom. Now if I let go, that's cutting out to protect itself. Turn it down just a touch. What 55 volts peak to peak. So you can't disagree with me. Anything over 55 volts peak to peak, I previously said in a note, 22 volts peak to peak per channel. And as it's heating up, that noise is coming back. The heatsink's getting warm. Well, the back of the amplifier is actually getting hot. Actually, it's getting very hot. This area here on the back of the amps is getting hot. We don't get the clipping as we do with the 8 and 12 ohm resistors, but it's definitely something's happening here. Now I'll turn this down. Now when I've got two scope probes set up, you'll get the positive going sine wave and the negative going sine wave on the other channel. When it gets to this 55 volts or 22 volts peak to peak, the top sine wave inverts and matches the bottom sine wave, which effectively cancels each other out. So you end up with nothing. If both sine waves are going positive at the same time on the resistor, then you've got no difference across the two. And it's consistent. They flip at 22 volts peak to peak. So this particular sub doesn't like this 4 ohm resistor. Oh, we can still get decent power out of it. So if I turn the equalizer up, there we go, that jumps up. Turn the volume back up. Turn it up slowly. There we go. See this noise. So obviously I've changed two FETs and you can't get hold of the originals. The two FETs I fitted have got an increased on resistance, on transconductance, and that 0.05 ohm resistor is a bit of wire. So how much difference that makes, no idea. So yeah, maybe this amp isn't a perfect replica of a brand new one, but EV do not make the schematics available. So this is the best I can do with this amp. Looking at the Hypex modular amplifiers, they're 200 watt amps. So you can't get like 600 or 800 watts out of two 200 watt amps. So we had 55 volts peak to peak. Divide by 2 to get just one peak. Multiply by 0.707 to get the RMS, equals 19.44, multiplied again by 19.44, so times equals, divided this time into 4 ohms. That's only giving us 94 watts. I'm shocked. So maybe there is a problem on this amp when driving a 4 ohm load. But as I say, there's no schematics, so I can't test it any further. So I recommend if you've got a 4 ohm woofer and it's cutting out, go to an 8 ohm because you can get 300 watts out of it. Maybe there's a problem on this amp. I will never know because there's no schematics. And I bet EV do not make those simple cheap amplifiers available separately. Whether Hypex do or not, that's another question. If Hypex make those amps available for the EV, leave a comment. And at 300 watts it's going to pack a nice tidy punch. So sorry if this is out of focus. So I don't know what to make of it. So Electro-Voice ELX118P. So the Electro-Voice bit, this front end, this isn't very sensitive because you need 1.5 volts to get the maximum power. A 450 Mackie will give you full power of 50 millivolts, not 1.5 volts. Designed and engineered by Electro-Voice USA. Yet this power supply and these two amplifiers are designed by Hypex here in the Netherlands. I say here in the Netherlands, here meaning we used to be part of Europe, but now we're not. So designed in Europe, in the Netherlands, just across the water. Hypex amplifiers, Hypex power supply. This bit is EV. And it's 300 watts RMS minimum, so it's not bad. Yeah, credit where credit's due, it has a reasonable amount of power. Unlike, as I keep on saying, the ZLX 12 and 15Ps. So not bad if you've got one and it's blown up. That's how you repair it. If you've got a short circuit, remove both of these, see if your supplies come up. Let me know what you think about the branding and the manufacturing. And it's still got a brand name on. Hypex, Netherlands. Anyway, hopefully you found this helpful. At least we could get this going. I've shown you what transistors to substitute these obsolete ones for. But yeah, not a bad amplifier. Cheap and cheerful. Although knowing EV, it's not cheap. And again, like the previous amplifiers, the schematics aren't available. Hopefully this has been of interest to some of you. Thanks for watching.